Okay, now we're trying to figure out the mass of New Caprica, and we're looking again at the forces on one of the moons. The force diagram and everything is the same as it was for the other one, so we'll just start with the F-net. G times the mass of the planet times the mass of the moon over that orbital radius squared, because that's the same as the distance between the two bodies, is the mass of the moon times 4 pi squared r over delta t squared. We're trying to figure out r in this case, so I'm going to solve this expression for r. I'll multiply the delta t squared up here, multiply the r squared up here, bring the 4 pi squared down, and cancel the m's. So gm delta t squared over 4 pi squared equals r cubed, so I want to take a cube root. When I plug in the numbers, I have to make sure I'm careful to put everything in SI units, kilograms, and seconds, or it won't come out as expected, because in the G, there's Newton meters squared per kilogram squared. The Newton, 1 Newton is a kilogram meter per second squared. So if we start putting in kilometers or days or something, we're not going to get what we're looking for. And if we do that, we'll get about 576,000 kilometers. Our moon is about 480,000 kilometers away from us, so it's in the right kind of ballpark. New Caprica is about the same mass as the Earth, a little bit bigger. Okay, so now we have this moon, and it's orbiting in a circular orbit, but it's going to come along now and be sped up by a collision. So it's going to go faster than it was before. You can think of it kind of like throwing a ball. If you throw it harder, if you throw it with a bigger speed, it's going to go further before it falls, right? So it's going to go further, and it's going to end up further away. It's still going to have to turn around, and it's still going to come back. And it'll be tangent with that point, and that same point at the orbit, but now it'll have an ellipse. And it's not a great ellipse, but that's the right idea. So there's our old one, and there's our new elliptical orbit. So this one is 45 days long. The question is this one 35 or 55 days long? Well, if I look at Kepler's laws, see that the delta t, the orbital period, is proportional to the semi-major axis to the 3 halves. So a bigger orbit will give me a longer period. And this definitely has a bigger semi-major axis. For a circle, the semi-major axis is just the radius. For the elliptical orbit, it's half the orbit, so about to there. Right? And that's the radius, which is the semi-major axis for the circular one. So this one's definitely bigger, so it will definitely have a longer period. And now that I know that, I can find the size of the new orbit. So I'm going to use that. I'm going to use Kepler's third and compare it to the old orbit. So delta t new is my new s divided by delta t old over that radius of that circular one, which we know from the previous one. As long as we know an orbit, we can use it to reference with Kepler's third. So what I'm looking for is the size of the new orbit. I'll find the semi-major axis to make that happen. So I'm going to take this 3 halves here, and I'm going to raise both sides to the 2/3. Delta t new over delta t old. So to the 2/3, and times r. So now I've solved it for that. And I need to plug in the numbers. As long as I use the same units, I'm okay, because we're in ratios. That's a great thing about ratios. So I'm going to go ahead and use just days. Just 55 days over 45 days here. And then I'll use my radius in kilometers, as I did there, and I'll get an answer in kilometers. And I get 778,300 kilometers approximately, which will be bigger than my old orbit, which is what it should be. So it worked out okay. All right, there you go.